In this video, we're going to look at electrophilic aromatic substitution in higher benzene rings, and we're going to look at heterocyclic rings, and then we're going to look at another type of aromatic substitution called nucleophilic aromatic substitution. Okay, so naphthalene itself, shown here, can do the electrophilic aromatic substitution just like benzene, and when you do electrophilic aromatic substitutions on an unsubstituted naphthalene, like this one, what you find here is that you get mostly what we call the one substituted isomer and very little of the two substituted isomer shown here. There's a mechanistic reason for this, and this has to do with the fact that if we were to add the electrophile to this double bond right here, we can get either of two regioisomers, one here where we form the initial carbocation right there, and the other regioisomer shown here where nitro goes to the 2 position and the carbocation goes over here to the 1 position. Okay, so the reason that we get this compound here as the major isomer has to do with the resonance stabilization of the carbocation intermediates. All right, so here are the allylic type resonance structures you can write for this carbocation. The first one is here. It'll now put the positive charge at the other 1 position. I guess this is technically the 4 position. And we can write a third resonance structure where we do the allylic resonance, and this would move it here. And we can write some more that would involve resonance stabilization in the other ring system. But that's, these 3 here will just illustrate the point. Okay, I want to add a little clarification on these 3 resonance forms. In the first 2 right here, we have not altered the aromaticity of the other ring. The other ring is still an intact benzene ring. However, this last resonance structure has destroyed the aromaticity over here. It's no longer aromatic. So this last resonance structure we're going to consider as really not as strong a contributor to the overall picture of this molecule as these other 2 right here. All right, when we go to the other regioisomer and we start drawing the same types of resonance forms, this is the first resonance structure we get, and recognize here that we have destroyed aromaticity. And when we draw the next resonance structure by just doing the standard allylic carbocation resonance form, we also get another resonance structure where this ring is no longer aromatic. So when you attack the 2 position, you get only 1 resonance form you can write that leaves the benzene ring intact over here, but your other two resonance forms have destroyed the aromaticity in this benzene ring over here. So in general, naphthalenes are going to substitute at the 1 position because the resonance forms that you get by substituting at the 1 position don't destroy the aromaticity in the other ring to the same extent that the resonance stabilization from attack at the 2 position requires that your resonance stabilization destroys the aromaticity in the other ring. Okay, so we can leave the other ring aromatic in most of the resonance forms from attack at the 1 position, and that's why we get preferential attack at the 1 position. Okay, all right, so that just says what I just said there. There it is in writing, okay? All right, let's look at heterocyclic aromatics. I'm going to use furan as the example here, but everything I say for furan goes for thiophene and for pyrrole as well. Okay, so when we do electrophilic aromatic substitution on furan, we have 2 possibilities. We can substitute at the 2 position shown here, and this is the major product. A minor product is the one that comes from substituting at the 3 position. All right, let's look at the reason here. All right, so when we start looking at the resonance forms here, when we attack the 2 position, we can draw initially this one. Now this is an allylic carbocation, so we can draw the standard allylic carbocation resonance form. But because this new resonance form here is directly beside a lone pair, we can also write a 3rd resonance form that delocalizes the positive charge to oxygen, and it's formally an oxonium ion where everything now has an octet. Okay, when we attack the 3 position here, the only resonance forms we can write are the one that the carbocation we initially get and the oxonium ion. Okay, so when we attack the 2 position, we have more resonance stabilization of our intermediate carbocation, and that's why we see attack at the 2 position for furan, thiophene, and pyrrole. Okay, another interesting thing about furans, thiophenes, and pyrroles is also that they're very activated in electrophilic aromatic substitution compared to benzene. And essentially what we've done here is that we've replaced one of the pi bonds. Okay, sorry, I forgot to turn that into Greek. Of benzene with a lone pair. And the lone pair is generally more basic, more nucleophilic than a pi bond, so that translates to these compounds here being far more nucleophilic or far more activated in electrophilic aromatic substitution than benzene itself. Okay, finally, we're going to look at another kind of aromatic substitution. All right, so a long time ago, when we were talking about the SN2 reaction, we stated that you could not do the SN2 reaction at a sp2 carbon, so halogens at sp2 carbon generally do not engage in the SN2 reaction. Okay, there's a variety of reasons. This is a stronger carbon-bromine bond than your typical carbon-bromine bond, and when you think about the trajectory of the SN2 reaction, here's where the nucleophile has to come. It has to come right like that. It has to basically pass through the middle of the benzene ring. Okay, so these don't do the SN2 reactions, but you can substitute certain aromatic halides or certain aryl halides. Okay, the reaction becomes possible if we have strongly electron withdrawing groups in the ortho and para positions, and the stronger the electron withdrawing group, the more facile this reaction. And the more of these groups we have in the ortho and para position, the faster the reaction as well. All right, so here we're treating this chlorobenzene derivative that has nitros ortho and para to the chlorine with methoxide ion, and here we see fairly facile substitution to give us the methoxybenzene derivative. In this last case here, we're going to treat this with an amine. Okay, so the amine can be a nucleophile here, okay, because it's got these lone pairs of electrons. Okay, mechanism isn't as simple as I wrote there. We're going to look at it in more detail in the next slide. We'll find that there's actually some intermediates here. But this reaction here would lead to the substituted benzene ring, the aminobenzene. Okay, all right, so one thing you'll notice here is that I used a fluorine, and we had stressed back in the nucleophilic substitution chapter that fluorines were not really good substrates for substitution reactions, but in this reaction they're pretty good. And this is not the SN2 reaction at all. It's mechanistically far more complex than just directly displacing the halide in one step. And one of the things that's kind of a giveaway here is the relative reactivity of halogens. Here, fluorine is best. Fluorine has always been notorious in all of our previous examples for not really doing anything. But here, fluorine is actually our most reactive substrate. Fluorine's more reactive than chlorine, greater than bromine, greater than iodine, but all of them are reactive. Okay, so here is the mechanism for this reaction. We're undergoing a slow step here where we're adding the nucleophile to the benzene ring to make a carbanion. Okay? All right, so the carbanion is now produced, and in the fast step, this carbanion is going to eject the leaving group to provide the substituted compound. Okay, so fluorine is the most reactive because it's the most electronegative halogen. Okay, so when we look at how much partial positive charge character we have at this carbon, that's highest for fluorine. Okay, and that's why fluorine ends up being the most reactive. All right, this fast step, loss of fluorine is not quite as favorable because it's not as good a leaving group, and it's got a stronger, the bond to carbon is much stronger, but this is occurring in the fast step, so it's not part of the rate equation. So fluorine helps out in the slow step. It hurts the fast step, but that doesn't matter because this is the rate determining step right here. Okay, why does it require that you have an electron withdrawing group on the benzene ring? And it has to do with the stabilization of this anion. Okay, so we're going to write allylic carbanion resonance structures in a similar way to how we were writing allylic carbocation resonance structures. Okay, we're going to just swap the positions of the double bonds and the lone pair. Okay, so we're going to turn this into a double bond and this into a carbanion. And we can write an additional resonance structure that puts the negative charge here. So as long as you have electron withdrawing groups ortho or para to the halogen, they're in exactly the right place to stabilize the negative charge. Recall that a dipole going this way is very stabilizing to a negative charge. It's very destabilizing to a positive charge, but very stabilizing to a negative charge because the negative charge at carbon means that carbon has too much electron density and you want to take some of that away. Okay? We'll talk about this later in stabilized carbanions. I think this is in chapter 20 in this textbook, but this carbanion resonance form that I've shown in blue is actually a resonance stabilized carbanion. We can delocalize the negative charge to one of the nitro group oxygens. So here is the nitro group drawn out. Okay, sorry, I've clearly forgotten that extra negative charge right there. Sorry about that. But yeah, so there's a net negative charge. A positive and two negatives give us a net -1 charge overall for this molecule. All right, so we can write a resonance form where we delocalize the negative charge to oxygen, like in this magenta resonance form over here to the right. Okay, and it's this resonance stabilization of the carbanion intermediate which really allows you to attack the ring in the first place. Okay, all right, coupled with the electronegativity of the halogen. All right, so I think this is the so we have one more problem here where we're going to rank these compounds here in terms of their relative reactivity towards sodium methoxide, the typical nucleophile. Okay, we're going to rank the most reactive as number 1 and the least reactive as number 5. And let me just tell you here that 2 of these compounds are actually really unreactive and aren't going to do the reaction at all. So we're going to say that number 4 and number 5 are really tied. Okay, all right, so we already know that bromobenzene itself, the one on the far left that has no electron withdrawing groups of any kind, is not going to be reactive, right? But if we start to analyze the halogen and the number of electron withdrawing groups in the correct ortho and para positions, we can sort of make a prediction as to what's going to be the relative reactivity here. All right, so here in this one we have one strong electron withdrawing group and it's para. Here we have two strong electron withdrawing groups. They're ortho, one's ortho, one's para, and we have a fluoride as our halogen. Okay, so we're going to rank this one. Let's just give them names here. Okay. All right, so we're going to rank C ahead of B because it's got a better halogen leaving group and because it's got more electron withdrawing groups. Okay, D also has two strong electron withdrawing groups, but it's got bromine as our halogen, so we're going to rank C ahead of D. And in the last one, all of our electron withdrawing groups are meta, so they're not really activating the system at all, and it's doubtful that E would be reactive to the sodium methoxide, but it might be more reactive than A because you do have the nitro group stabilizing the anion, but still it's sort of orienting to the wrong place. The nitro groups are telling the OME to attack here or here or here, ortho or para, to the nitro or cyanide groups, okay, and not where the bromine is. All right, so here's our final ranking. We're going to say that C is our most reactive because it's got more EWGs and the halogen is more reactive. D is number 2, less reactive halogen. B is number 3, still activated for nucleophilic aromatic substitution, but it's only got one electron withdrawing group. By the way, having electron withdrawing groups is probably the bigger factor that's more important in the relative rate than the identity of the halogen. Okay, so having more electron withdrawing groups in the correct place is the more important factor. Okay, all right. As far as 4 and 5 go, probably both of them are unreactive. We might expect there to be more of a reaction with 4 or with E, but not an appreciable reaction. So A and E are probably both unreactive. Okay, so this is where this video is going to end. The last video is going to be a series of synthesis problems. Okay, so we're going to stop that here, I think. Yep, okay. All right.